All right, so here we're in chapter 14, and last time we talked about sort of intermolecular forces and also phase changes. So remember that when we talk about intermolecular forces, those are the forces that hold together um, different molecules. So there are basically a few different types that we talked about, and basically the way that they work is a really basic sort of idea that opposites attract, electrostatic attraction. So again, the negative side of one molecule will be attracted to the positive side of another. And there are, in terms of intermolecular forces, what's known as hydrogen bonding, which is a relatively strong type of intermolecular force. And that again is a bond between hydrogen and nitrogen, oxygen, fluorine. And again, you do need that sort of bond there for it to have the ability to hydrogen bond. These are typically polar molecules that have that ability that will hydrogen bond. Now, when you get to polar molecules that really don't have the ability to hydrogen bond but are polar, you get more of what's referred to as a dipole-dipole interaction. And dipole is the same idea as the dipole moment for polar molecules. And basically what that means is if it is a polar molecule, it pretty much has this situation happening. It will always have a positive side to the molecule, always have a negative side to the molecule. No matter what you do to it, nothing's going to change in terms of that. And what that means is it's good to go in terms of interaction. So it doesn't have to rely upon something happening. So this is also a relatively strong intermolecular force. And this is really the force that polar molecules that do not hydrogen bond use. And then we have dispersion forces, and dispersion forces are pretty much your weakest intermolecular force. And these are really the main and sort of only sort of force that nonpolar molecules use. Now, all molecules can use some type of dispersion forces, but it's not going to be their main source of it. But for nonpolar molecules, it is going to be the main force, and it's going to be the weakest. Again, as these interact, it affects things like solubility. It affects things like melting points and boiling points. The stronger the intermolecular force, the higher melting points and boiling points that you have. The weaker, the lower the melting points and boiling points you have. We also talked about as well in this chapter sort of phase changes in a heating and cooling curve that we kind of looked at, something like this, where you had like ice and water, a liquid state, and steam up here. And remember that at certain transitions, and if we use water as an example, 0 degrees Celsius and 100 degrees Celsius, there is a transition of state that occurs at those points. And you can see here that the temperature line is flat, which means it does not change temperature, but will change phase. And as you go from, say, this guy here, this is the delta H of fusion. And that is the energy required to do nothing more than take a substance from solid to liquid, or liquid to solid at the melting point or freezing point. And again, it is the same number regardless of which way you're going, but the sign will be different if it's an endothermic process or an exothermic process. So if it's going from solid to liquid, you got to put energy in. So that's an endothermic process. The number should be a positive number. If you're going from liquid to solid, it's an exothermic, energy has to be released, so it should be a negative number. Also, as you go from liquid to gas or gas back to liquid, that's the delta H of vaporization, it is referred to, or the heat of vaporization. And that again is the energy required to just change the phase of a substance from liquid to gas at its normal boiling point. Once again, we use these guys a lot of times in conjunction with, a overall process that's happening. We looked at these curves as we saw, and we did in a couple of those examples. If you're in any of these sort of green areas, You are in the same phase, but you are changing the temperature. So if you wanted to figure out the heat associated with that, that goes back to our specific heat equation that we used before. And you could add up the total amount of energy required. For example, I think maybe we did ice to steam or something like that. And again, it's just these different sort of steps along the way that you want to do. Remember, though, if you're sort of doing this equation here and it is not liquid water, for example, the specific heat capacity will not be 4.184. So you might have to obviously use the appropriate one. As we saw, ice and steam is about 2 rather than 4.184. Any questions on any of that stuff that we talked about there? All right, then we're just going to talk a little bit about solids, and not too much about solids, but just a little bit. And there are many substances formed what are known as crystalline solids, and these are guys with regular arrangement of their components. There's two types. There's ionic solids, like something like sodium chloride, and there's molecular solids, something like sucrose, which is sugar. A third type of crystalline solid contains atoms of only one type of element covalently bonded to another, and that's known as an atomic solid. Graphite, carbon, boron, silicon, and all the metals. Now, typically when things go into their solid phase, they lose a lot of energy. And remember, as we also talked about, there may be positive guys or negative guys, or positive sides or negative sides to molecules. So again, when they sort of slow down, they do sort of move around to sort of maximize that attractive forces. And as we talked about, sort of minimize areas where maybe, you got positive guys near positive guys or negative guys near negative guys are parts of molecules as you look at it. So here's sodium chloride. And again, it's a really organized, ordered sort of arrangement. Some of these solids have such order that you could just take a little piece of it and you basically could rebuild the entire structure just from like a little snapshot of the structure, as it's very repeatable in terms of the pattern. Here, the chloride is the larger circles because they gained electrons. The sodium are the smaller ones because they lost electrons here. And again, they maximize that sort of attractive forces by trying to keep a good distance between anything that is of a similar type of charge. Now, here again are some examples of it. We have our diamond over here, which is basically carbon, and in that arrangement there, we have our sodium chloride, which is our ionic solid, and then we have something like ice here. And as we talked about with the hydrogen bonding, and as it slows down in terms of energy, they really don't get super close to each other, and it actually creates these sort of pockets of open space in the ice molecule, and that's what we saw as we talked about that. That's why ice has actually a lower density than, say, liquid water, which is an unusual sort of characteristic of something like water. When we talk about bonding in solids, ionic solids are held together by strong forces of oppositely charged ions. That's electrostatic attraction. That electrostatic attraction is pretty much the strongest attraction you could have, or one of the strongest attractions you could have. And that is why these things have very high melting points. So you could heat the heck out of an ionic solid. It will not go into the gas phase because it's held together. There's really, really strong forces. Molecular solids are held together by dipole-dipole forces or dispersion forces, and they melt at lower temperatures than ionic solids because really the ionic solid is held together by sort of an intramolecular force. These are more intermolecular forces, as we talked about, and they're always weaker than any intramolecular force. So ionic bonding, even covalent bonding within a molecule is going to be a weaker attraction than an intramolecular force, intermolecular force like dipole-dipole. And again, that is like two water molecules together, coming together here. Now, when we talk about metals, there's a couple of different types of alloys. An alloy is a substance that contains a mixture of elements. There's a substitutional alloy where basically some of the host metals are replaced by some other metal of similar size, like sterling silver, 93% silver, and 7% copper. Interstitial alloy is formed by when you actually put in these holes that happen between the different atoms, and you put other metals in those holes. For example, steel contains carbon atoms in the holes between the iron as well. And that's what you see here. So brass, for example, we have kind of substitution of some of the copper with some zinc guys, giving us that alloy. Here, again, in steel, you got some little carbon type atoms there between the different iron atoms and the holes that sort of form there between the different atoms. All right, that is it for that. That's a very short little solid talk. All right, we are then off to 15 here. All right, chapter 15 is about solutions. Again, solutions are aqueous, homogeneous mixtures, and they are the ones that get that aqueous symbol, as we talked about probably a number of times up to this point. Again, there is a difference between liquid and aqueous. And once again, a liquid is typically a pure substance, like water by itself would be a pure liquid. This is really a mixture, and it's a homogeneous mixture. And if you took something like water and again put some salt in it, the salt would dissolve in the water and you would make a sodium chloride solution here. So really something that's aqueous is usually made by taking something and dissolving it in another part of it. Now, when we talk about aqueous solutions, they're important in a lot of reactions that take place. And when we talk about solution, which is, as I just mentioned, a homogeneous mixture of two or more substances, there's basically two parts to the solution. There's the solute, which is really the smaller part of the solution. And there's the solvent, which is the larger part of the solution. So in my example I just did there, where we had water and our sodium chloride, our water here would be our solvent, and the sodium chloride here would be our solute, making again our sodium chloride solution. How do you know what the solute is? It's pretty much the name of the solution. So if you have a sodium chloride solution, that is the solute. If you have a potassium chloride solution, then potassium chloride is the solute. Water is a very common solvent, and it's good for a lot of things, especially ionic things and polar things. It works really well. Water is not always going to be the solvent, but it is in a lot of cases. Water, again, would be, as we'll talk about, a terrible solvent for something that's nonpolar, for example. But if you have something that's ionic, you have something that is polar, then water in a lot of cases is going to be probably your solvent of choice because it will work really well. But just keep in mind, sometimes people think water is always the solvent. It can be other things depending on the situation. As what we just was talking about, water is again a very effective solvent, and that is because water again is polar. So because water is polar, where the oxygen side is more negative, the hydrogen side is more positive, it works really well for ionic compounds because ionic compounds are ions basically. So you got a positive ion, you got a negative ion. And water, because it's polar, has a positive side and a negative side, which allows it, as we've perhaps mentioned before, to basically interact well with these ions. For example, the positive ion would interact with the oxygen on water, which is negative, given it that sort of opposite attraction that's occurring. And water's hydrogen side, which is its positive side, would interact with, say, the negative ion. And that's going to make ionic compounds really soluble in water. They actually do what is referred to as a ion dipole interaction, and that's an intermolecular force similar to dipole-dipole, but it's basically the ion and a dipole. That is what allows something, for example, like sodium chloride to dissolve. And it may look like it has sort of disappeared or went away. But what happens again is a lot of water molecules basically surround each of the ions. So much water molecules surround them that you can no longer visually see the sodium or chloride ions basically floating around that solution. It's surrounded by a lot of water. We know again that they really didn't go anywhere, and this is a mixture because I think we did it earlier on in lab and stuff like that. If you take some salt water and you evaporate it off and heat it up, all the water molecules will evaporate, and that will leave the ions there to come back together, and you'll see the solid reappear. And again, that is a mixture because nothing changes. Everybody's still there fundamentally the way they were originally. They just appear to be different. That process where the water molecules basically surround an ionic compound and help it dissolve is what's sometimes referred to as hydration. As I mentioned before, just these water molecules allow those ionic solids basically to sort of dissolve. And again, you can't see it anymore. They also prevent, in a sense, this really strong attractive force between these ions from coming back together. They almost act as a buffer to prevent those ions from coming back together. And that's why, as we just talked about, when you do heat up water, what happen or in an ionic compound like this, like sodium chloride in water or salt water, you get rid of all the water molecules as they evaporate off. And at that point, there now is really nothing in the way of these two ions finding each other. And that's why, again, you see the solid come back because they're just going to go, cool, no more water. They're going to clump back together and the solid again will reappear, say in your evaporating dish or something like that when you do that. So this is the process, again, just so much water molecules present that they're able to basically pluck off, this is your ionic solid, these ions from the solid. You help it out a lot because typically when you go again to dissolve something, you take something and you stir it, right? So as you stir it, you're adding energy. You're also throwing a ton of water molecules all over that solid, and that's going to initiate the process of it dissolving a lot easier and a lot quicker than if you just kind of dropped it in there and didn't do anything with it. So you dropped a lot of water molecules all over the surface area, and they basically start plucking off these ions surrounded by water. And that's basically what this shows here. Again, those water.
An ionic solid dissolves in water because of its polar nature. Notice how water molecules become attached to the ions of a sodium chloride crystal in the process called hydration. Positively charged sodium ions attract the partial negative charge of the oxygen in water. A similar attraction occurs between negatively charged chloride ions and the hydrogen atoms, which have a partial positive charge. These interactions loosen the attractions between the ions in the crystal, dislodging them from the crystal. Additional water molecules surround the released ions, insulating them from attraction to other ions.
And again, they're able to sort of overcome that really strong intermolecular force or intramolecular force of electrostatic attraction because, again, there's just so many water molecules, so that kind of interrupts the process. So as we talked about, ionic bonds are between metals and nonmetals, and the attractive force there is electrostatic attraction, which is opposites attract due from the loss and gaining of electrons. Obviously, we also talked about covalent bonding over the chapters, and that's usually our two nonmetals together where we're sharing electrons. Um, and really, these intermolecular forces are really important uh, factors in how basically molecules interact with each other, how things are soluble or are not going to be soluble in our cases. Obviously, polarity, as we talked about in the bonding chapter, is based on overall unequal sharing of electrons in a molecule. Again, a unsymmetrical geometry will usually result in that. Ultimately, in a bond, it is the electronegativity of the two atoms, right, to determine whether or not you're going to have a polar bond present or not. And that's also really important in terms of how molecules can interact with one another. You can, as we will see, and we maybe talked about as well, you can have a molecule that actually is sort of has two parts that are like nonpolar back here and a polar part up here. And the presence of that sort of bond within this molecule does allow something like methanol, which is what that is, and we used it, I think, in that experiment, uh, to interact well with something like water. So, the presence of even a bond sometimes in a molecule that is mostly nonpolar, but just having that polar bond will allow it to interact well with something, say, like water. So let's talk a little bit about solubility in water. So ionic compounds are definitely soluble in water, as we just saw. Again, they're able to do that opposite attract, that ion dipole interaction that occurs. But there are non-ionic compounds that are also very soluble in water, things like sugar, things like ethanol. Ethanol looks just like methanol that I just drew, but it has one more carbon, basically. So it looks like this. And again, that is ethanol. And once again, here with ethanol, we do have this carbon hydrogen part that's nonpolar. But once again, we do have this polar bond here. And that polar bond is pretty much the exact same bond that we see in water. And because of that, the positive side of one can interact with the negative side of the other, and it can hydrogen bond with each other, as they both have a hydrogen that's bonded to a nitrogen, oxygen, or fluorine, oxygen in this case. And that makes something like methanol that I drew on the previous page and ethanol really soluble in water, because they both are using basically the same intermolecular force that they use with themselves. So water hydrogen bonds with other waters. So when you bring something like methanol in or ethanol in, that's also going to hydrogen bond, it works really well. Also, it's not an incredibly large molecule, so it doesn't get in the way. So just that present, that OH bond makes it very soluble in water. I will say that if you build out this part of the compound with more carbons and hydrogens, somewhere around 4 or 5 and above, the solubility will get really, really low in water, even though it still has that OH bond. And that's because the molecule gets bigger, and it also, the nonpolar part gets bigger, and it just gets in the way of water being able to interact well with it. So if you have something that sort of has a nonpolar part, but that OH group, and it's relatively small, about 4 or less carbons in it, it will usually be fairly soluble in water. But again, if you get a lot more carbons in it, even with the OH group, the solubility drops a lot. With that being said, also, if you have a lot more OH groups, for example, in a molecule, that gives that molecule multiple places it can interact with water, and it also increases the solubility, because everywhere there's an OH group, it allows an opportunity for water to interact well with it. And that's sort of the case with sugar. Sugar is a relatively large molecule, but what sugar has for its advantage is it's pretty much littered with OH groups all over it. So it has a lot of OH groups all over it. So even though it's a relatively larger sort of molecule, all those OH groups really increases the solubility with water. And as we know, if you take sugar in water, it will dissolve with no problem. And it's because of the presence of all those OH groups. And that's what we see here. Again, methanol and water able to hydrogen bond, which again is a relatively strong type of interaction and makes them quite soluble in each other. And there's ethanol doing hydrogen bonding as well. Now, what about oil and water? Do they mix? The idea there is no, they really do not. And the reason for that is oil is essentially just a long old chain of carbons and hydrogens, basically. I won't draw them all, but it actually keeps going, believe it or not. But it's just a long carbon hydrogen chain, basically. That is how they get other kinds of oil products out of these things. These are really, really long carbon hydrogen chains. They do what is known as thermal cracking. They crack it up into smaller pieces like octane, and you get gas that you put in a car and all those kind of things. So these are all carbons and carbon bonds, carbon hydrogen bond. This is pretty much as non-polar as you could get when you look at something like oil. And the reason it doesn't mix well with water is water, again, is polar. So it really boils down to those intermolecular forces. Something like oil, which is nonpolar, it's going to exclusively use dispersion forces, which are those weak intermolecular forces. Water is going to want to do some hydrogen bonding because that is the way it sort of rolls and it's able to do so. So those are two very, very different types of intermolecular forces, hydrogen bonding being the strongest, dispersion forces being the weakest. So when they get together, there really is kind of no way for them to maintain that interaction over a long period of time. If you remember, dispersion forces are forces that really has to rely upon something happening for them to get those charges, like the electrons go to one side of the molecule or another, creates an instantaneous dipole, or something comes near it that has a charge and kind of temporarily gives it a charge, but they won't be able to maintain that. So over a long period of time, they really will sort of separate out. And again, if you've seen an oil spill in the ocean, the oil ends up just floating on the top of the water because they do not mix and stuff like that. Again, something like oil and vinegar or salad dressing, right? You can mix it up really well, right? And it's mixed. But if you leave the bottle kind of sitting undisturbed, eventually what will happen is everything will kind of separate out from each other. And that's again because they can't maintain that interaction over a long period of time. But for a short period of time, because everybody could do some type of dispersion forces, they can interact for a very short period of time, but there's just no way to maintain it and keep those bonds basically happening. And the other problem with oil is, again, to have anything dissolve basically in water, you have to replace water-water interactions with similar types of interactions. And oil is a relatively big sort of molecule. Water is a relatively smallish molecule. So it also just is big and clunky and gets in the way. It doesn't fit in with a lot of water molecules and allowing them to interact. That brings up the idea, as we talked about when we were talking about that lab, of like dissolves like. And that's basically the idea that things that use the same type of intermolecular forces with themselves and find somebody else that uses the same type of intermolecular force, they will be soluble in each other. So that is, again, typically when we talk about things that will be soluble, ionic things and polar guys, they will be able to do some type of ion dipole. Polar and polar things will be soluble in each other. They could either do hydrogen bonding or dipole-dipole. And also nonpolar things and nonpolar things will be soluble in each other. They both will be using dispersion forces. The only trouble you have, as we have seen in terms of insoluble, is when we cross over polar and nonpolar. Not so good. They will not mix again because they're using very, very different types of intermolecular forces. Questions on that there? So here is sugar, and as I said, it's a relatively larger molecule, but one thing that helps it is everywhere, pretty much, there's an OH group, as you can see, is pretty much littered with OH groups. It will allow it to be really, really soluble with water because water can interact at all those points. Here you can see this is pretty much our oil, nothing going on there but non-polarness there, and that's straight dispersion forces, which again, not going to work well. Will work really well with a non-polar solvent. Like I think we use heptane in that experiment, or hexane, which is also basically just 6 carbons in a row or 7 carbons in a row. So those guys, you know, if you wanted to do something that's non-polar, you would want to use something that's a non-polar solvent with it, and they both will be using dispersion forces, and that will allow them to interact well. So that's why water is a very common solvent. But it doesn't work well for a lot of things, but it works good for ionic things and polar things. But once again, if you try to dissolve something in water that's non-polar, like I think we did the iodine crystal we tried in water, it will not dissolve because, again, opposite sort of attraction intermolecular forces. There's our oil, which is typically what happens. Eventually, the oil layer will be up on top. The water layer will be on the bottom. Now, when we talk about solubility, when one substance is dissolves in another, is said to be soluble. So if we take some type of solid like salt and dissolve it in water, it will be soluble. If one substance does not dissolve in another, is said to be insoluble. So we take some oil and mix it with water, it won't dissolve. If we took some of that potassium permanganate crystal that we did and we mixed it with hexane, which is nonpolar, it will not dissolve either. There is a limit to the solubility of one substance in another. Gases are always soluble in one another. And that's because if you just think about gases, they are flying around, which means just by that definition, they are constantly mixing with each other because they're flying around each other. Some liquids are also mutually soluble, so polar and polar, nonpolar and nonpolar liquids will mix well with each other. So that idea of like dissolves like is really important. As I mentioned, those intermolecular forces is really the main thing that you look at to see whether or not you would expect these things to interact well with one another. Now, the solubility of a solute in a solvent is dependent on temperature. Typically, the higher the temperature, you'll have a larger solubility of a solid in a liquid. And they sometimes tell you if you're having a hard time, for example, dissolving a solid in a liquid, you could just warm it up a little bit, and oftentimes will help it. The solubility of one compound in another is dependent on temperature. So usually with increased temperature, you get a greater solubility because when you increase the temperature, you're actually adding more energy. And that more energy allows everybody to have a little bit more ways to break apart from each other and start the dissolving process. At a lower temperature, you also typically will have a lower solubility of a solid in a solvent. At a lower temperature, there's also a larger solubility of a gas in a liquid. So if you have a liquid with a gas at a lower temperature, that gas molecule is going to fly around a lot slower, and it would take longer for it, for example, to escape the liquid part. The solubility of gases also depends on pressure. So the higher the pressure, the larger the solubility we have of a gas. And that's because Boyle's law, right? A little P1 V1 equals P2 B2. As the pressure goes up, the volume goes down, and vice versa there. So at higher pressures, we have a really small volume. And that means that our gas molecules are near each other. And just by that presence of them being really close to one another, they're going to constantly be mixing with one another and be soluble in there. Now, there is a limit to how much solute you can get to dissolve in a solvent. If we add too much solute to a solvent, we could create what is known as a saturated solution. And a saturated solution is one where basically at that particular temperature, you've hit the maximum amount of solid that will dissolve in that solvent. If you add any more solute to it, it will not dissolve. It basically will just start piling up at that point. So at some point you could take sugar and water, and at some point you'll hit the point where that sugar basically stops dissolving. And at that point you definitely have a saturated solution. It's known as hitting the saturation point at that point. The opposite of that is what's known as an unsaturated solution. And in an unsaturated solution, you really haven't hit that point yet. So you haven't hit the saturation point, which means if you take more solid, it will continue to dissolve, and it will continue to dissolve until you hit a saturated solution. So you could have an unsaturated solution that will continue to dissolve solid, continue to dissolve solid until you hit a saturated solution. At that point, obviously no more will dissolve.
The flask contains a supersaturated solution.
And this is the demonstration we did the other day, which is a supersaturated solution. And that is a solution that is basically a saturated solution made at a higher temperature. And as we talked about, because it was sort of made at a higher temperature, that allows more solid to be dissolved in it because it's at a higher temperature. So the solubility of sodium acetate, for example, that's here, is going to be much higher at that larger temperature. What they typically do, as I talked about, is they'll heat it up, they'll get all the solid to dissolve, and basically they'll let it cool back down. Problem with letting it cool back down at that point is as you let it cool back down, the solubility of what's dissolved in there changes, and it actually gets a lot less should be dissolved in there. The problem is you've already dissolved it at this point, and what you created is, as we talked about, a fairly unstable solution that if you just take one little crystal of what you dissolved in it, that'll be enough for all the solid to come out. And that again is what we saw in person. We'll take another look at it here.
Sodium acetate in water. A small crystal of sodium acetate will be added to the solution. Focus your attention on the portion of the solution to which the crystal is added. Here is the process again in slow motion.
Super slow motion replay. There it is. And again, that's what we saw. So basically, just that one little crystal, you could barely even see it, was enough to cause all that solid that had been dissolved in it to basically come out of solution for it to realize that at this particular temperature, it should not have that much solid in there and basically have too much and it all comes out.
The flask contained
As we saw there when we did it, that obviously goes from a sort of liquid state to a rock hard solid state as all that solid basically precipitates out of solution. Now, a couple other ways to describe solutions is concentrated, and a concentrated solution has a relatively large amount of solute dissolved in it, and a dilute solution, which has a relatively small amount of solute dissolved in it. Usually we buy solutions a lot of times as a more concentrated solution, and we do a dilution process to make it more dilute like what we use in the lab. Again, just a real life example of that. Obviously, we've all probably done it. Got like a beverage at the AM, PM, or wherever it may be, and you got ice in your drink, and you drink it, you come to class, but leave it in your car, you come back, and all your ice melts, right? And you go taste your drink afterwards because you go figure how bad could it be. And you go, that does not taste as good as it did when I went in, right? And that's because obviously all the ice melted and all that water diluted it, created a lot more solvent in that case to your solute, which was your soda, basically syrup and all that carbonation as well. So we're going to talk about some important percentages, or some important concentration units. And the first type of concentration unit is what's referred to as mass percent, or percent M/M. And this is one way that we could describe a solution's concentration. The mass percent is the mass of the solute divided by the mass of the solution times 100%. Now, the important part of this is the bottom part here, which is the mass of the solution. Remember that a solution is two parts. It is the solute and it is the solvent. So you do want to make sure that when you do this calculation, that you actually get the mass of the solution and not what is a very common mistake that people make, which is they get the mass of the solvent. The reason that's a common mistake is very common in these questions. They give you that information separate from each other. So they'll give you like the mass of the solute, they'll give you the mass of the solvent, and a lot of times people just go with the mass of the solvent, but you do need to, a lot of times, add those things together to make sure you get it. If you had a 4.5% by mass sodium chloride solution, you could actually turn that into sort of a conversion factor or a usable conversion factor. And basically what that would mean is you have 4.5 grams of sodium chloride in 100 grams of solution. You could also use it in the opposite way, where you go 100 grams of solution would contain 4.5 grams of sodium chloride. So sometimes you are given the mass percent in a problem, and sometimes it's easier a lot of times to take a more dimensional analysis approach, and you can convert it into a conversion factor and use it as a conversion factor. And all you have to do, and why that's sometimes easier, is you also just remember is opposites cancel. So you can just look at units, get the units to cancel, and it'll actually do the math of the formula for you. You could obviously plug it into here and solve for whatever you're looking for as well, but you could also take that more dimensional analysis approach. Now, there's other types of percent concentrations that we also come across. This is percent volume to volume. So that's volume to volume. And that is the percent volume to volume is the volume of solute divided by the volume of solution times 100%. So typically speaking, milliliters over milliliters is typically what we roll with on that one. There's also percent mass to volume, which is percent mass to volume, the mass of the solute divided by the volume of solution times 100%. Almost like grams per milliliter, like density, basically. Yeah. Bless you. Just like the other ones here, if you had a 4.5% volume to volume sodium chloride solution, that would mean you have 4.5 milliliters of sodium chloride in 100 milliliters of solution. You once again can flip it around the other way. 100 milliliters of solution would give you 4.5 milliliters of sodium chloride. And if you had 4.5% mass to volume sodium chloride, you would have 4.5 grams of sodium chloride in 100 milliliters of solution. Or in 100 milliliters of solution, thank you, you have 4.5 grams of sodium chloride in this case. So you could use these as conversion factors. And sometimes, again, like I said, it's a lot easier than using the formula and stuff like that. I would say on these, you don't have to be so careful with the bottom part here. I would say that in a lot of cases, in a lot of problems, they just give you the volume of the solution. You don't have to like add them together or anything like that. So just really the mass percent is the common one that you sometimes need to do. All right, so let's take a look at an example here. A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. Calculate the mass percent of calcium chloride in the solution. Okay, so let's take a look. We're looking for the percent mass to mass here. And that is the mass of the solute divided by the mass of the solution times 100%. In this case, we have 2.5 grams of calcium chloride. That's going to be our solute. That is the smaller part here. Water would be our solvent, which is the larger part of the solution. So our mass of our solute will be 2.5 grams. The mass of the solvent will be 50 grams. Now, remember here on the bottom, we need the solution, which means to get the mass of the solution, we need to add those guys together, basically, and that gets us 52.5 grams. So to calculate our percent mass to mass here, again, you don't want to divide by just the 50, which is just the solvent here. We want to go 52.5 grams times 100%. That's going to get us there, 2.5 divided by 2.5. 4.76% mass to mass, and you can put calcium chloride if you like in that case. Any questions on that calculation? So again here, super common. People just kind of divide by that on the bottom and forget to add them together. So just watch that there in this calculation. Let's take a look at another one here. Perhaps a concentrated hydrochloric acid solution contains 37.2% by mass HCl. What is the mass of the HCl that's in 35.5 grams of that mass? Which can give us, again, our mass of our solute divided by the mass of the solution times 100%. In this particular case, they gave us the percent mass to mass. That's 37.2%. We are looking for the mass of the solute here. And we know that the mass of the solution is 35.5 grams. How do I know that 35.5 grams was the solution and not the solute? Because we are looking for the mass of the HCl. And remember that pretty much the name of the solution is the solute. So if you're looking for how much HCl you have in an HCl solution, then that's going to be the mass of the solute. And that's how I know the other one is really the solution. So you have a couple of options here. Obviously here you could just plug and chug into the formula if you like, and you could solve for the mass of the solute. Again, you can also take a more dimensional analysis approach here. And that's what I'm going to do here just to show you. You could take the percentage that was given to you, and basically what that would mean is there's 37.2 grams of HCl in 100 grams of solution. Or again, you could flip it around and use it like a conversion factor in the opposite direction. 100 grams of solution would contain 37.2 grams of HCl. So since I do have the mass of the solution here, 35.5 grams of the solution, remember opposites attract when we do dimensional analysis, or opposites cancel. And that would give us 37.2 grams of HCl over 100 grams of solution. The grams of solution would cancel, and we'll end up with 37.2 times 35.5 divided by 100, 13.2 grams of HCl. That, by the way, is the same if you popped it into the top here with 37.2% equals the mass of the HCl divided by 35.5 grams times 100%. You multiply and then you divide. A little bit more rearranging that you have to do on that one here. Just doing a dimensional analysis way, it just kind of takes care of the math for you by doing opposites cancel. It does the dividing and multiplying for you in a sense of setting it up that way without having to worry about it. Any questions on that one there? All right, the next really important unit of concentration, which is probably the most commonly used unit of concentration, is molarity. And molarity is capital M, and it does stand for moles per liter. It is really the moles of the solute over the liters of solution. You could think of this really as a formula, like the density formula as well, because we oftentimes will really solve for any of these three things. So again, if you wanted liters, that would be moles divided by molarity. Or if you wanted moles, that would be liters times molarity. So very commonly we rearrange this guy and really solve for any of these three things. You should always, when you are using molarity and by itself and volume, it does need to be in liters, the volume, for it to properly cancel out. That is because if you have a 4.5 molar solution of sodium chloride, what that really means is you have 4.5 moles per liter of sodium chloride. And again, as I talked about when we were doing the lab and some other things, I would definitely recommend that when you are doing a calculation that you convert it into those two units, and so that way you could visually see it. because probably very common mistake, people, when they see that big M, all they think about is moles. They don't even think about the liters part of it or the volume, not really sure where it is, if they should be multiplying, dividing, or whatever it may be. So this way, at least you could see both units, and you really could use it like a conversion factor. So you could use it like moles over liters. If you needed to, you could also flip it on its head there and go liters on top and moles on the bottom. So you can use it really if you have the molarity like a conversion factor, and really take, again, a more dimensional analysis approach to the calculation, which will help you rearrange these equations easier as well by doing opposites attract. The number always stays with the moles part, and it's always 1 liter. So the bottom guy never, or the liters, never has a number. It's always assumed to be 1, basically, in this case. Now, when you have a solution that is 1 molar, it does represent that it has 1 mole of the solute per liter solution. And when we talk about ionic compounds, because ionic compounds are strong electrolytes, when they actually dissolve in water and you have a molarity of it, you can also look at what the molarity of each of the ions are, for example, in it. So if you had 1 molar sodium chloride, that would be 1 mole solid sodium chloride in a liter of solution. It contains 1 molar sodium ions and 1 molar chloride ions as well. How do we get that? Well, if you take something like sodium chloride, when it's really in solution, it does not stay together, and you will get sodium ions floating around, and you get chloride ions basically floating around. And basically, if this is 1 molar, you could take a dimensional analysis approach. And when we look at this is a 1-to-1 relationship in terms of the sodium ions, how it breaks apart. How that affects the concentration is you take 1 times the 1 molar, which means you would have 1 molar sodium ions floating around in that solution. You could also do that for the chloride. It's a 1-to-1 relationship as well, which means you would take 1 times 1 molar and you would have 1 molar chloride ions. So sometimes you're not interested in maybe in the entire ionic compound together. Maybe you're interested in the concentration of an ion that's floating around in a solution, and this is how you could relate it. Now, if you had something like calcium chloride, when that breaks apart, you get a calcium ion, and you also get 2 chloride ions in this case. And if the calcium chloride had a concentration of 1 molar, if we were looking at just the calcium, it is a 1-to-1 relationship between them, which means we would take 1 times 1 molar, and we would end up with 1 molar calcium ions. Now, if we were to look at the chloride, it is a 1-to-2 relationship. So you get twice the chloride ions as you do calcium in this case when it goes for a swim. How that affects concentration is we'd actually multiply it by 2. 2 times 1 molar would give us 2 molar chloride ions in this case. What that basically says is it is twice as concentrated in chloride ions as it is in calcium ions. And that is again because when you put that guy in there, it is a 2-for-1 special. You get a calcium ion and a couple of chloride ions. So you got twice the amount of chloride for every calcium. So it's twice as concentrated basically in chloride as calcium. That is different than for sodium chloride. When you do that, it's a 1-for-1. You get basically the same sort of concentration that's going to happen in that case. That is the short way to figure out the concentration of an ion. You can basically just kind of do a mole-to-mole relationship. And if it breaks apart into a 1-to-3 relationship, you would multiply the molarity by 3. Obviously, the molarity is not additive. 2 and 1 doesn't equal 1, but that is the way you do it. The long version of this calculation is this. You would take the 1 molar calcium chloride, and you would do an actual mole-to-mole relationship. So mole-to-mole relationship, but 1-to-1, 1 mole of the whole thing gives me 1 mole of the calcium ions. Moles of the whole thing cancel. gives me 1 mole per liter of calcium ions. If you did it for our chloride, it is a 1 to 2 relationship, mole relationship. So for every 1 mole of the whole thing, you get 2 moles of the chloride ions here. Moles of the whole thing cancel, gives you 2 moles per liter of chloride. This is why we multiply by 2. This is why we multiply by 1. So that's really the long version of why you multiply by 1 or 2 or 3, whatever the coefficient is. You're basically doing that multiple relationship, and that's how we get there. Question on that there. So as I mentioned before, sometimes you're just interested in maybe the ions that are floating around, maybe not the whole thing, and that's how you can relate the concentration of the whole thing to just the ions. A standard solution is a solution whose concentration is known accurately, and a standard solution like what we were just doing in that lab or would have made in that lab is what we're talking about there. So why don't we calculate this here, calculate the molarity of a solution that's prepared by dissolving 15.6 grams of KBr in enough water to make 1.25 liters. Potassium will go with 3910 and bromine 7990. Here we have grams that we can get to moles, so that's good. And obviously here we have liters. So we do need to actually convert our grams into moles, which is a very common conversion. Also very common is converting milliliters to liters, 1,000 milliliters to the liter. That's also a very common conversion. So we'll do that first. We'll get our grams into moles here, KBr. Looks like we just need to add those together actually. So we'll go 3910 plus 7990 by 119 grams per mole. So from the periodic table, using the molar mass, 119 grams per mole of KBr. Grams will cancel, and we will end up with 0.131 moles of KBr. That is, again, the top part. Our bottom part is good to go. So to find the molarity here, 0.131 moles divided by 1.25 liters. And we'll end up with 0.105. Now, in terms of units, they do not cancel, so you can leave it as moles per liter of KBr. Again, the number stays with the moles part. You could also, at this point, if you wanted to, convert it back into big M KBr as well. So that's, again, another way that you can kind of state the answer in this case. Question on that one there. All right, let's take a look at one last one here to wrap it up. What is the mass in grams of sodium nitrate is required to make 2.5 liters of a 0.15 molar solution of sodium nitrate? Sodium 2299, nitrogen 1401, and oxygen 16. Okay, so let's take a look. Obviously, we're dealing with molarity here, which is our moles per liter. In this case, we do have the volume of 2.5 liters, which is this guy. Here we do have the molarity given to us, 0.15 molar. Remember that I'm probably going to use a more of a dimensional analysis way, get rid of the big M, and that is 0.15 moles per liter. Again, so I can see both of the units that are present. And I do have this one. So if we want to rearrange this, moles would equal, in this case, liters times molarity. The reason we want moles is we could then get to grams that way by using the molar mass, right, from the periodic table to do so. Now, You could obviously plug and chug into the equation, but again, if you take a more dimensional analysis way, you don't even have to worry about the rearranging part of it. You just got to roll with opposites cancel. So I have 2.5 liters using my molarity with both units showing moles per liter, opposites cancel. So those guys would cancel, and that will give me my moles here, 2.5 times 0.15. 0.375 moles of sodium nitrate. And again, when I say opposites attract, because you could use this if you needed to, like this, but obviously the way it was written was the way that we needed it to cancel out. That again did pretty much the rearranging for me without having to rearrange it myself. At this point, what I need is the molar mass here from the periodic table, and that is 2299 grams per mole for the sodium, 1401 for the nitrogen, plus 3 times 16 there for the oxygen. Going to get me 85 grams per mole. So to get us how many grams, that would be 0.375 moles of sodium nitrate. Using our molar mass from the periodic table here, we do want grams up on top so that we end up with grams. And we'll take moles on the bottom so that they cancel. And we will end up with approximately 31.9 grams of sodium nitrate would be needed. So if you were going to make the solution, you would scoop out about 31.9 grams of this, mix it with some water because it's ionic, it should dissolve. Enough water to get a total volume of 2.5 liters. If you mix it really good, you then would have a solution that has that concentration of 0.15 molar. Any questions on that there? All right, we're